You know the feeling. It's like 2 a.m. Your monitors are casting that super familiar blue glow across the room, right?
Oh, yeah, the classic late night debugging ambiance. Yeah.
Exactly. And you're just staring at a terminal and you're hesitating for just a second before you run an NPM update.
Because you know exactly what's going to happen.
Right. You know dependencies are going to conflict or, a package will deprecate. And suddenly your perfectly stable build is just throwing massive walls of red text.
Yeah, but I mean, we accept that risk, right? Because as engineers, we generally understand the mechanics of package management. We know what's under the hood.
Right, we do. But right now, as software engineers, we're doing something that is honestly far more reckless.
Oh, absolutely.
We are swapping out foundational AI model API endpoints in our tech stacks as if they're just, generic utility functions.
Yeah, treating these massive trillion parameter neural networks like they're just interchangeable black boxes.
Exactly. You just change the base URL in your config file, you swap the API key, and you just sort of assume the entire intelligence layer of your application will keep humming along.
Which is a terrifying assumption when you really look at the mechanics.
It really is.
Huh?
So welcome to the deep dive. The server logs are rolling. The coffee is still somewhat warm.
Barely warm at this point, but yeah.
Fair enough. And today, we're looking at a huge stack of nodes covering Claude, Gemini, and really the broader model wars happening right now.
Because if you're writing code today, you are just constantly bombarded with new model releases.
It's relentless. It feels like every Tuesday there's a new announcement, a new launch, some new claim to the benchmark throne.
And it gets overwhelming, even for people building in the space full time.
So our mission today is to just cut through all that hype cycle.
Yeah.
We're going to decode what these releases actually mean for your architecture.
Right, helping you understand the fundamental structural differences between the major AI models.
Moving past the marketing buzz, seeing the true landscape. Because underneath those uniform REST APIs, the engines powering these things are completely different.
They are radically different. And if you don't understand those differences, you're introducing this massive architectural risk straight into your code base.
Okay, so before we even look at the literal wiring, the neural networks, we have to look at the philosophy driving the build.
Yeah, the strategic bets.
Exactly. The major AI labs are not just taking that same transformer paper from 2017 and trying to optimize it in a vacuum.
Right, they aren't just doing the same thing with different logos.
No, they're making very distinct, calculated strategic bets. The sources we're looking at today point out 5 major players and their specific vectors.
So we have OpenAI, and they're betting heavily on just raw speed and massive scale.
Right. Then Anthropic is betting basically everything on safety and alignment.
Google is placing its chips on data and their existing infrastructure advantage.
Which is massive. And then Meta is going all in on open source ecosystems.
And finally, you have companies like Mistral betting on raw computational efficiency.
And when you think about it, it feels identical to the early days of cloud computing, doesn't it?
Oh, that's a great comparison. Yeah, totally.
Like think about AWS, Azure, and Google Cloud Platform maybe a decade ago. Everyone was trying to solve the exact same broad problem.
Right, hosting your applications, scaling your compute.
Yeah, but they chose completely different vectors to dominate that market. Like AWS went for that first mover, massive infrastructure scale.
And Azure leveraged all its enterprise relationships to integrate seamlessly with, the existing corporate stacks that were already there.
Exactly. While GCP leaned hard into high-end developer tools in Kubernetes.
And the cloud you chose dictated how you structured your entire DevOps pipeline.
Right. But here's my question for you. Are these AI strategies just PR narratives? Like, are they just spun up by a marketing department, or do these philosophies actually alter the compute layer that you and I are interfacing with?
Oh, they absolutely alter the compute layer. I mean, fundamentally.
Really? Like right down to the hardware?
Yes, think about it. If your core bet is scale, like OpenAI, you spend your capital aggressively acquiring H100 GPUs, building these massive data centers, and just pushing the boundaries of raw parameter counts.
So you're basically solving for generalized capability through brute force.
Exactly. But if your bet is open source, like Meta, your engineering constraint is totally different. It's consumer hardware.
Because people need to actually run it on their own machines.
Right, so you invest heavily in hyper-optimizing models, quantization techniques, architectural tweaks.
Because an open source model that requires a $20 million supercomputer to run isn't very useful to the general developer community.
Exactly. The philosophy literally dictates the architecture from the ground up.
Okay, let's follow that thread directly into the code base then. Let's look at how these strategic bets manifest under the hood.
This is where it gets really interesting.
Yeah, our sources highlight three specific architectures here. We've got Anthropic's constitutional AI, Google Gemini's native multimodality, and the mixture of experts approach used by Mistral and DeepSeek.
Let's start with Anthropic.
Yeah, let's do that because as a developer looking at this, I actually have to push back a bit on Anthropic's approach.
Okay, lay it on me.
So they're betting on safety, right? Traditionally in the industry, that means RLHF, reinforcement learning from human feedback.
Right, where you train a reward model based on armies of human contractors, basically rating the responses.
Exactly. Thumbs up, thumbs down. But Anthropic swapped that out for constitutional AI, where the AI essentially grades its own outputs based on a set of rules.
Got a constitution, right?
Right. But wait, if a model is inherently prone to hallucination, and we're asking it to grade its own hallucination based on a text prompt constitution, aren't we just building a massive compounding feedback loop of garbage?
That is such a common reaction.
I mean, how is that actually safer than human oversight?
Well, you're hitting right at the core of the alignment tax debate there. But you have to look at the scaling laws.
Okay, how so?
RLHF simply cannot scale to the volume of data required for these newer frontier models. Human preference is highly subjective, it's really slow, and it's wildly expensive.
I guess that's true. You'd need millions of hours of human labeling.
Exactly.
Yeah.
Anthropic recognized that if their foundational bet is safety, a human-in-the-loop bottleneck would just eventually kill their development velocity entirely.
So constitutional AI shifts it to AI in the loop.
Yes. The model generates a response, it critiques its own response against the explicit principles in its constitution, and then it revises it.
But doesn't that just happen at the prompt level?
No, that's the key. This happens during the training phase. It actually modifies the loss function to penalize outputs that violate the Constitution.
Oh, wow. So it's a true architectural shift.
Exactly. You aren't just filtering bad outputs at the API wrapper level. You are fundamentally altering the gradient descent process.
So the model's latent space learns to intrinsically favor the Constitution. Okay, that makes a lot of sense, actually. They changed the training mechanism to align with their behavioral constraint.
Yep. The philosophy becomes the math.
Let's pivot to Google then, because their constraint is different. Their bet is capturing and utilizing the world's data, really leaning on their massive infrastructure.
Right, the data advantage.
Yeah. And the sources highlight Gemini's native multimodality. Now, the industry has had multimodal models for a while.
Sure, for years.
Usually you train a text model, you train a separate vision model like CLIP, and you essentially just stable them together.
Yeah, they communicate, but they are very distinct systems.
Right. So what does native actually mean here at the tensor level?
It means bypassing that whole stapled together bottleneck entirely. When you staple models together, you're translating an image into a text description, right?
Yeah, like generating a caption and feeding that to the LLM.
Exactly. And you lose an incredible amount of granular data in that translation. Native multimodality means Gemini was trained from day one, from the very first epoch, on text, images, audio, and video simultaneously.
Wait, simultaneously. So they're projecting all those totally different data types into the exact same dimensional space.
Yes. The audio waveforms, the image pixels, the text tokens, they are all mapped into the same shared latent space.
That's insane.
It is. The loss function is literally optimizing across completely different data distributions at the exact same time.
The infrastructure required to do that must be staggering.
So it's massive. You have to ingest and process massive, dense video files right alongside sparse text data, keep all the gradients stable, and train a single unified transformer block to understand the relationships.
Like natively understanding the relationship between a visual concept and a textual concept.
Exactly. It proves Google's infrastructure bet is baked right into the literal wiring of their architecture. No one else really had the compute to do that from scratch.
Which brings us to arguably the most developer-focused bet, right? Mistral and DeepSeek's obsession with raw computational efficiency.
Ah, mixture of experts.
Yes, MOE. We hear this acronym thrown around constantly in the community. Let's really unpack the mechanics here. how does this actually solve the inference cost problem for developers?
Well, consider a traditional dense neural network.
Okay, like a standard llama model or something.
Right. A dense model means that for every single token you process, every word you send or receive, every single parameter in the entire model is activated.
So the math is executed across the entire network every single time,
Exactly. If you have a 70 billion parameter model, you are doing 70 billion calculations for a simple query like, print hello world.
which is terribly inefficient. I mean, you don't need the entire neural network's knowledge of 16th century French poetry to write a Python function.
Exactly. It works, but it takes a massive amount of VRAM and computational energy. Mixture of experts changes the graph architecture itself.
How so?
Instead of one massive, dense network, the model is divided into several smaller, specialized subnetworks.
The experts.
Right, the experts. And sitting in front of them is a routing network.
Okay, so a router decides where the prompt goes.
Close, but it's token by token. When a token comes in during inference, the router applies a softmax function to determine which specific experts are best suited to handle that particular token.
Oh, I see. So it might route your coding question to just 2 out of the 8 available experts.
Yes. So you get this concept of sparse activation.
Sparse activation, okay.
Hmm.
So the total model sitting on your server might be huge, say 47 billion parameters total.
Right, which means you still need the VRAM to hold all the weights in memory.
Yeah, but the active parameters being used for the forward pass on any single token might only be like 12 billion.
Exactly. You get the broad knowledge base and the reasoning capability of a massive model, but the inference speed, the latency, and the FLOP's cost of a much smaller one.
For a developer building an application, I mean, that is critical.
It changes the unit economics entirely. It means you can host a highly capable model much cheaper, and your users get way faster responses.
So, again, the strategic bet on efficiency directly dictates that token-level routing architecture.
It's all connected.
Okay, but since these models are all architecturally distinct, I mean, they're processing data differently, routing tokens differently, optimizing totally different loss functions, the natural engineering question arises.
Which one is the best?
Exactly.
Yeah.
How do we objectively measure which one is actually the right tool for the job? In software engineering, we live and die by metrics.
We really do.
If I'm picking a relational database, I run a benchmark. I test the read and write speeds, I check the latency under load, I look at the hard numbers, and I make an informed choice.
Right, it's deterministic.
Yeah. But our sources are flashing a massive warning sign here. They're saying benchmark scores for these frontier models are actually an unreliable guide to real-world quality.
It is arguably the biggest trap for engineers right now. Yes, we are treating LLM benchmarks like traditional software benchmarks, and the analogy just completely falls apart.
Why is that?
There are three main structural reasons. The first one is data contamination.
Okay, meaning the models have already seen the test data during their pre-training phase.
Exactly. Think about famous benchmarks like Human Eval for coding or MMLU for general knowledge.
Right, those data sets are totally publicly available on GitHub and the open web.
And these models scrape vast, indiscriminate portions of the internet, like the Common Crawl, for their training data.
So they just hoover it all up.
Yeah. So by the time a new frontier model is tested against a standard benchmark, there is a very high probability of n-gram overlap between the test questions and its training corpus.
Wow. It's like evaluating a student's intelligence by giving them a test where they accidentally memorized the answer key the night before.
That is the perfect analogy. They aren't demonstrating generalized reasoning. They're literally just regurgitating memorized tokens.
That makes the leaderboard score completely meaningless for my actual application.
Pretty much.
And I imagine the second issue is just how narrow the measurements are, right? Like a benchmark like MMLU is basically a static, multiple-choice trivia test.
Exactly. It's testing fact retrieval.
But when I'm building an AI feature, I'm not asking it trivia. I'm dropping it into a dynamic, agentic workflow.
Right. You need it to actually do things.
Yeah, I'm asking it to read a messy proprietary codebase, maintain context over a long conversation, format its output in strict JSON so my backend can parse it, maybe execute an API call.
And a static multiple choice test tells you absolutely nothing about how a model handles those complex prompt chains.
Nothing at all. Doesn't capture the friction of the real world.
And that leads directly to the third issue, which is optimization pressure.
Oh, because the market treats these scores as gospel.
Yes. Developers and investors look at these benchmark scores as definitive proof of superiority. So the AI labs are under immense pressure to win them.
Right. Goodhart's law. When a measure becomes a target, it ceases to be a good measure.
Exactly. The labs are just teaching to the test. They are actively optimizing their models to perform well on specific, famous evaluations.
So you might see a model that scores incredibly high on a popular coding benchmark.
Because it was heavily trained on isolated, perfectly formatted Python function completions, yeah.
But then when you drop it into your actual IDE and ask it to untangle 5 years of undocumented tech debt and spaghetti code.
It completely hallucinates and falls apart, yes.
So if I'm a developer trying to build a reliable application and the public scoreboards are essentially just contaminated marketing material, I can't just guess which model to use.
No, you definitely can't.
I have to build my own evaluation pipelines. Like I have to take a subset of my actual production data, my specific prompt chains, and run them against the different APIs to see which architecture handles my specific constraints best.
Building custom automated evils is becoming a mandatory part of the modern developer toolkit. You simply cannot rely on a generic leaderboard anymore.
Which brings us to the market reality.
Okay.
Because if there is no single, objectively best model that dominates every single task, what does the future of this space actually look like?
Well, the sources point out a fascinating dynamic happening right now. Frontier models are converging in raw baseline capability,
Okay.
but they are radically diverging in how they are deployed.
Meaning the sheer intelligence of these top-tier models is plateauing somewhat.
Yeah. Whether you are using Claude 3, GPT-4, or Gemini Advanced, they are all getting very, very good at standard reasoning, writing, and coding.
So the noticeable gap between the smartest model and the second smartest model is shrinking.
Rapidly shrinking.
That's actually great news.
Hmm.
It means we aren't all just going to be paying a mandatory tax to one single megacorp for our intelligence layer.
Right. The market is not going to be a winner-take-all monopoly. It's developing into an ecosystem of specialized models.
Because they all have different architectural bets, so they're going to fit into completely different layers of your tech stack.
Yeah.
I can see exactly how this orchestrates in a production environment. Let's say I'm building a customer service platform.
Okay, sure.
I might take a hyper-efficient open source model like Mistral and run it locally on my own bare metal servers, just to do basic data extraction, intent classification, sorting, that kind of stuff.
Right, because it's cheap, it's incredibly fast because of that sparse activation we talked about, and you're not paying API network latency.
Exactly. But then for a much more complex reasoning task, say, analyzing a user's secure financial history to authorize a refund, I route that specific prompt out to Anthropic's Claude.
Ah, because you need its strict constitutional AI safety guarantees for that highly sensitive action.
Yes. So you're orchestrating an ecosystem.
You're acting as a conductor of different neural networks, leveraging their architectural strengths and mitigating their weaknesses.
And the sources emphasize that this ecosystem approach isn't just a technical reality. It introduces a massive geopolitical dimension to our architecture choices.
Oh, absolutely. This isn't just about latency and VRAM anymore. It's about global power dynamics.
Right. The countries and the companies that control frontier AI will actively shape regulations and power structures for decades to come.
Which makes choosing an open source model versus a closed source API a much heavier decision than just looking at the pricing tier.
Right. But we have to view this impartially as engineers.
Right. Always. You have to recognize that technology embeds the values and the regulatory frameworks of its creators.
How so? Give me an example.
Well, an open source model allows anyone, anywhere, to download the weights, modify them, and run them locally without any external oversight.
Which, from an engineering standpoint, champions freedom of innovation. It guarantees data sovereignty.
Right. You don't have to send your users sensitive PII across international borders to some API hosted in another country.
But the flip side, the reality of an open source model, is that it lacks enforceable guardrails once deployed.
Sure.
Bad actors can download the exact same weights, strip out any alignment training, and use it at scale for malicious purposes. And there's no centralized API provider that can pull the plug on them.
That's the risk. Conversely, a tightly controlled, closed-source model allows a company, and by extension, the regulatory framework of the country that company resides in, to enforce strict safety guidelines right at the API level.
So they can prevent malicious use, filter out specific types of content, monitor for abuse.
Exactly.
But then, as the developer, you are completely dependent on their subjective definition of safe and malicious.
You're trusting a black box controlled by someone else's legal and cultural framework.
And if an LLM is the reasoning engine of your new application, The guardrails of that LLM literally dictate what your application will and will not do.
Exactly. If their API decides to silently filter a response based on some brand new internal safety policy, your application logic just breaks without warning.
Wow. So when you integrate a foundational model, you are deploying a system of values and a specific regulatory worldview right into your production environment.
Yes. Because these models are being developed across the globe with radically differing priorities on safety, efficiency, openness, and control, the architectural choices you make have a ripple effect far beyond just your monthly cloud bill.
It fundamentally evolves the developer's role, doesn't it? Like,
Yeah.
we aren't just writing deterministic logic anymore. We are evaluating and selecting cognitive engines based on our project's constraints and our users' needs.
Which is exactly why understanding those initial strategic bets, scale, safety, data, open source efficiency, is so vital. You simply cannot treat them as identical tools in a utility library.
Man, this has been a deeply practical look at the mechanics driving these platforms. And tomorrow, we're going to keep this exact momentum going.
Oh, I'm looking forward to it.
Yeah, we are zooming in on one of the most important yet widely misunderstood technical dimensions differentiating these models: context windows. We will explore the mechanics of how a model actually remembers information in a massive prompt, the attention mechanisms involved, and why simply having a million-token context window isn't the magic bullet for RGRAG applications that everyone seems to think it is.
It's a crucial topic, especially as developers push the absolute limits of what these models can process in a single pass.
Definitely.
But before we sign off, I do want to leave you with a final thought to mull over, building on that idea of orchestrating multiple models that we just talked about.
All right, let's hear it.
So if the market is moving toward this mixed ecosystem and you are building a system that chains these different architectures together, consider the system-level liability.
Okay, what do you mean?
Well, imagine you use a hyper-efficient open source model to parse an incoming user request, but it subtly hallucinates a parameter.
Okay.
That hallucinated parameter is then automatically routed to a tightly controlled, closed source agent that has been granted tool execution privileges on your database.
Oh, no.
And the closed source model flawlessly executes the flawed command. When the system breaks or user data is compromised, where does the fault lie?
Wow.
As an engineer designing these mixed model pipelines, how do you build fault tolerance when you are combining a system optimized for freedom with a system optimized for execution?
That is a heavy architectural question to keep you awake tonight.
It really is.
The next time you go to swap an API endpoint, remember what's actually running under the hood. Thank you for joining us on this deep dive. Keep questioning the defaults, keep building, and we will catch you tomorrow night.